So in this lecture, we will essentially talk about single component, one component systems. And we'll see what kind of transformations are affected. So essentially we'll be looking more into physical transformations, not chemical changes for the moment. Now, before we can describe these, what exactly is the phase, what are these components, and why do we need them, let's try to give you a fair idea of what a phase is. For example, solids. Yeah. If I have two solids mixed together, sand and salt. Okay, sand itself is too complex. Salt and sugar. Then we have a two-phase. We have a two-component system, salt and sugar, and we have two phases. One is the salt phase, one is the sugar phase. On the other hand, if I have some alloy, yes.
So would it still remain a two-phase system if we are able to distribute salt and sugar homogeneously?
Okay, so now it was just salt and sugar. You take water, good. You take water and you dissolve everything in it. That becomes a single phase system. Now, how many components do I have over here? Water, sugar, salt. One must be careful, it's not salt, it's actually sodium plus and chloride minus. So, now, with this knowledge, is it a 3 or a 4 component system? How many of you stick to 3? How many to 4? No? I heard many of you. At least. No. So the thing is that although we have sodium plus and chloride minus, they are exactly the same number of charges. Yeah? The same number of sodium plus and chloride minus, so as to maintain charge neutrality. Although you are absolutely right that we should have 4 components, but for purposes of defining, I need to define only 3. Yes? So if I define sodium plus, I know chloride minus. So although a component that way we have 4, but for our purposes we need to define only 3. Right? So we'll also say that the number of components is 3 in this case. Good that you asked that. Now I was actually talking of the solids. But if in case, so like that, right? In case of liquids which are miscible, they make a homogeneous mixture. So no matter I pick up the liquid from here or I pick up the liquid from this position, I'll get exactly the same composition of the liquid. That's a homogeneous mixture, so it's a single phase system. The number of components, as you know, a sugar solution or a salt solution, we've just seen what the number of components are. In case of gases, they all mix together. Very homogeneous. If I have gas A here and gas B here, you've already seen the entropy of mixing was positive. So they are all homogeneous systems. So it's always a single phase system. The number of components will depend on the number of gases I have. Likewise, if you have an alloy which is homogeneous on the microscopic level, so no matter where I pick up the system from, it is thoroughly mixed together, then that alloy would also be a single phase system. Again, the components would depend on how many of these metals I have added. So it's like you have to be a bit careful when you're deciding the number of phases. The colloids, for example, would have a few different phases out there. So one has to be careful about that. And with a bit of experience, you'll be able to say what is a single phase system, what is a multi-phase system, 2 phases, 3 phases, so on and so forth. Okay, like I have written an example over here. Calcium carbonate solid goes over to calcium oxide solid plus carbon dioxide gas. Now clearly, I have 3 components over here. Calcium carbonate, calcium oxide, carbon dioxide. Anybody who has not done this experiment? No? Never? Or at least seen this experiment? सफेद नहीं होती आजकल घर में? हाँ, whitewash, yeah. So you have calcium carbonate, and you heat it. Okay, you don't do this experiment, right? You just take calcium oxide and mix it with water. Huh? You heat this, you get another solid. Now these two solids are not homogeneously distributed. So we have two of these components in two different phases. One is the calcium carbonate, one is the calcium oxide, and the third phase is your gaseous phase. So, like these, you can see many examples, and try to find out how many phases are there, how many components are there, because that's important to know when you want to study equilibrium. Remember, what we're going to do in the next couple or three, 4 classes, whatever we have for thermodynamics, is to concentrate on equilibrium processes. So now, the good thing is that at equilibrium, delta G is 0, right? There's absolutely no change in dG. Well, if I think of phase transformations, I need to introduce something. Already you know VdP minus SdT. dG is VdP minus SdT. But that's for a closed system, where my number of molecules does not change. My composition does not change at all. But if I think of phase transformations, let's say going from the liquid to the vapor, then some of the molecules are escaping from the liquid going all over to the gaseous phase. If condensation occurs, it's the other way around. So let's think of liquid going to the vapor phase. So let's say a small number of molecules, Dn, go from the liquid to the vapor. So what I'll write is Dn is equal to, so this is the number of moles. Number of moles being exchanged, let me just put it like that. Now, if I think about the change in the Gibbs free energy, then let me define something called the molar Gibbs free energy, that is Gibbs free energy per mole. So, and say that some of it is coming from the liquid to the vapor phase. Yes? So, the change would be the molar Gibbs free energy of phase 1 minus molar Gibbs free energy of phase 2 times the number of molecules, the number of moles, sorry. Right? The change in Gibbs free energy in phase 1 is equal to the Gibbs free energy, the molar Gibbs free energy of phase 1 times the number of molecules that have escaped from here minus the Gibbs free energy of phase 2 into Dn, which is the number of molecules that have come to this phase.
It's going from 1 to 2.
Sorry?
It's going from phase 1 to phase 2.
Phase 1 to phase 2. You want to write 2 minus 1? It's okay. Still will be 0. Okay. Now, this molar Gibbs free energy has a particular name called the chemical potential. So I'll write mu1 minus mu2 dn. That's called the chemical, or mu is the chemical potential. Right? So so the definition that I'm giving you is for a single component system, and in the next couple of lectures you will see how it changes when you have multi-component. So for the moment, the chemical potential is nothing but the molar Gibbs free energy, right? As the name suggests, it's a chemical potential, it's kind of a potential. So if one of the mu's was lower, so in phase 1 if it was lower, and phase 2 it would become higher. Right? Then things would have started to flow towards phase 1. Right? Dg is negative of processes spontaneous. So in this case, when you have equilibrium, then your chemical potentials in various phases everywhere is going to be equal. So at equilibrium, chemical potentials at all points are the same, or chemical potential at all points is the same. Right now, yes. So at equilibrium, the chemical potential at all points is the same for that particular component. Okay. So if I have two different components, right? Let's say I have some hexane and water, liquid, and it's in a closed container. So hexane and water are also in the gaseous phase. Then the chemical potential of water in the liquid and the gas phase are the same. The chemical potential of hexane in the liquid and the gas phase are the same. But chemical potential of water is not equal to the chemical potential of hexane in vapor or liquid phase. Okay. So if that is the case, then perhaps I can, make a general phase diagram. So a phase means that how things are transformed, right? That would tell me, the entire phase diagram would tell me how one transformation occurs from one phase to the other. And if you think about it, what are the variables that could cause these transformations? Pressure, temperature. So a phase diagram would be plotted between pressure and temperature, right? And I'm sure you've looked at some example of this. Solid, liquid, gases, that's your triple point, T3, that's your critical temperature. So there's no boundary between the liquid and the gas above the critical temperature. Well, what essentially happens is, you take a closed container, keep on, so let's say we have some liquid over there, and T3, the triple point, this is not a phase diagram for water, by the way, okay, it's a bit different, but just taking the example of water, T3 is 273.16 Kelvin, this is something, and something we always forget, this is also very important.